Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to a new discussion which is we are going to have on shaded relief models or hillsides and how we can apply how these are very useful for various kinds of studies. This is also one of the derivatives of digital elevation model, but now instead of derivative 4 or 5 I thought that I will put a completely separate name, because I have always found this hillside or shaded relief model very useful for various representations and various applications which I am going to discuss in this lecture. As this I am using both terms like hillshading and shaded relief model. Earlier people were very comfortable with shaded relief model, but later on few people started using hillshading. And no issue, we can use any of these terms, meaning is the same, that a hillside is a grayscale 3D representation of the surface. Of course, the input is a digital elevation model, and what it extra is here that with sun relative position taken into account for shading the image. So, because it is not illuminated, your digital elevation model, a typical digital elevation model is not illuminated by a source, a light source. What we do in hill shading, we take a light source or you can say a position of the sun, and we simulate that when if sun is in this position, how the terrain would look from the top, and that is what we get the hillside. So, this hillside or shaded relief model basically, as I have just mentioned, that simulates the cast shadow or cast the shadow thrown upon a raised relief map, because digital elevation model is representing a rugged terrain, might be, and more the rugged terrain, more the convincing shaded relief model you can generate. But if terrain is flat, then that may not be good for the eyes, but still it is very useful. For example, if I am having a digital elevation model of a like Thar desert, I may not be very see many of dunes and different kinds of aeolian features. But when I or landforms, but when I use a shaded relief model, that is a derivative from a digital elevation model, I can start seeing my these various types of dunes or some other landforms and can interpret them very easily. So, that is why shaded relief models or hill shadings are very useful. So, what basically we are doing that more abstractly upon the planetary surface represented. So, that means the digital elevation models can be created for any surfaces, and the position of the illumination source or the sun's relative position we can decide by ourselves what should be the position. So, the shadow normalies follow the normal convention, and that is normal convention is always lighting or illumination source being kept in top left, in which the light source is placed near the upper left corner of the map. Now, there might be some question that why only top left, why not in other, for which you definitely require a complete separate discussion, which is my one of the most popular lectures is a false topographic perception phenomena, in which I have explained that why it is kept in top left. But very briefly I would say that if illumination source and viewer, if both are in the same hemisphere, that means illumination source should always come from opposite direction. This is how our brain assumes. If it is not coming from opposite direction, then brain cannot perceive valleys as valleys and ridges as ridges. What they will perceive? Our brain will perceive valleys as a ridges and ridges as a valleys. That means a completely inverse topography, or I would call as false topographic perception. And since it's a phenomena, so we gave a name false topographic perception phenomena. But for time being, let's assume that by default all these softwares will bring illumination source from always from the top left corner. Now, if a map is oriented with north at the top, the result that the light appears to come from the northwest. So, this light will always be coming from that. However, this is unrealistic. Why unrealistic? Because we know that sun can never reach in the northwest. Sun will start from east and will set in the west. So, how a sun will reach on the north? But because we are working on computer, so we can simulate the sun position in terms of its with reference to north as well as the elevation as per our requirements, as per our desire. Though that might be unrealistic as here, that because the sun does not shine from the northwest direction. Therefore, the normal convention is followed to avoid this false topographic perception phenomena. Now, in many literature you may not find a discussion related with like this point, and that point like why it is kept in the top left, because many times they just mention the in the literature, especially in the books or in software manuals or helplines, but they will not tell why. So, that why part I have already explained to you, because of false topographic perception phenomena. Now, hill shading is an effective technique to basically to convert a 2D map or terrain surface into the 3D appearance. Though it is already a digital elevation model, a typical digital elevation model is already bearing the Z values. But if I am not using, then I am representing in a 2D form. But if I use that one Z value and then create a shaded relief model or hillshade, then I am using that the Z value as well. So, generally it is achieved the shaded relief model by a single point source of illumination. Now, here this point is very important, is the single, because we have been always assuming that there is only one sun, though even in our modeling or simulations, even when we do the hill shading, we always assume that there is only one source of light. But as you might have seen in during the night time cricket matches or football or other thing, if there are 4 sources of lights, you see 4 shadows. So, is it possible that also in our simulations from 2D to 3D, can we go for multiple source of illumination rather than single point source? That we will discuss little later. So, this what generally, as I have mentioned, that northwest light from 45 degree and it is measured with reference to north. So, it would be like this. And the elevation angle you can choose, generally it is also kept say at 45 degree. If I have to compare my digital elevation model or the shaded relief model with the satellite image of that particular area, then what I can do, I can know the sun position of satellite image when it was acquired, what was the sun position in terms of azimuth and elevation angle. I can use those 2 parameters of the sun and put here. But remember that in case of satellite images, sun will never come in northwest. So, what we can do, instead of generally sun will be in the southeast quadrant. So, what we can do, we can add 180 degree to the position of our satellite image and can shift 200 there. So, this is how you can simulate sun at in northwest direction. Currently what we are discussing is single point source illumination, but we may also think now of multiple point source illumination. So, how it is basically that the cosine of the angle between dm between a surface normal, which is as shown here, and a vector representing the illumination direction like this one here, and which defines the gray values of each surface units. So, this will define what should be the gray value, because this gray values, when they are different for different sloping surfaces, then only you can create a shaded relief model. So, if with this sun position, if a slope is facing complete sun, it will be highly illuminated. But if a slope is just opposite of that sun direction, that would be in the shadow. So, that is how once you are having shadow and illuminated surfaces or slopes like this, then you start feeling the or appearance of 3D from a digital elevation model after this processing. So, here the relative shading is decided based on the cos theta, and the details are here like this. So, where the theta between the incident light vector S and surface normal n, between this is the theta which we are talking. Now, here this is the example of 8-sided hill shaded pyramid. This is what the typical currently the softwares are following, this concept that illumination source is though here in the northwest quadrant. So, that is why it is highly illuminated, since it is having some degree. So, it is not 100% white, and this is not also 100% dark, but it depends what is the height of the sun and of course, the slope also. So, illumination source direction, as I have already said, is in the northwest direction in this scenario. So, 8, because like aspect, the similar things we follow here also. So, if we start thinking in terms of the values of a digital elevation model and how it is done, again this kernel of 3 by 3 will be used, because it is basically again a neighborhood analysis. So, how this will work, that I am having input raster, and here I am having the values. For simplicity, values have been kept, the cell values between 1 to 3, and of course, one cell is also having no data, which is marked as a gray. So, if input is having no data, output will also have no data. Further, output will also not have any data along the boundary, one cell thick boundary all along your output. So, only for that area in the center area, excluding the that area, you will not have. And as you remember that 7 cells out of 8 cells should have a value. If any of that 3 by 3 kernel for the center cell calculation, because otherwise there are 9 cells. So, for center cells calculation, we are looking the 8 neighbors. So, among these 8 neighbors, at least 7 cells should have values, and even more than if in a case when you are having more than 2 cells are having no data, then no calculation will be done. And that is why here what you are seeing here is no data is being replaced for that particular center cell in the surroundings. In the northern side there were no data. So, the hill shade raster has an integer value ranging from 0 to 255. It is always represented in gray shades, though you can with some techniques you can convert them in colors also, which I have also demonstrated earlier through a demonstration of software. So, the analysis of the shadow is done by considering the effects of local horizon at each cell, and the raster cells in shadow are assigned a value of 0. And the Z factor, again Z factor will keep coming in our discussion, that Z factor is essential for correct calculation when the surface Z units are represented in units different from the ground units, that is XY units. Now, hill shade parameters, what you are having here is the primary factors when creating a hill shade for any particular location in the location, that is the location of the sun in the sky, and two parameters will come, one is azimuth, another one is elevation. So, both are in angles or in degrees. So, azimuth is the basically angular direction of the sun measured from north clockwise. So, north will have 0 or 360 degree and azimuth of 90, that is towards the east, and the default azimuth in most of the softwares is 315, that is northwest corner or northwest quadrant. So, because if it is not kept and suppose it is kept in the southeast corner illumination source, then you would have a difficulty of perceiving things completely different. So, that is why that care has to be taken. So, it is always illuminated by default 315. You can check various softwares, in the default they will have, including in ArcGIS, they are having the default value as 315 and elevation value as 45 degree. So, the default sun azimuth is 315 in hillside, whereas in case of altitude or elevation, the altitude is the slope or angle of the illumination source above the horizon. The units are in degree from 0, that is parallel to horizon, to 90 degree, that is overhead, and that happens only in generally in noon time, depending on where you are located and what is the season, and default in the software is 45. So, for azimuth 315 degree, for altitude or elevation 45 degree. These are the default values. So, like here this value is kept at 45. Now, the example which we are going to cover, because as I have already said that if sun is in the opposite quadrant, and then the other areas will have completely in shadow. So, azimuth is the same in the each image, in these two images, but what has been done, the change in the altitude or elevation has been done. So, if as you know that when sun is near horizon, you would have large shadow, and when sun is overhead, you would have minimum shadow or virtually no shadow, should not have even a shadow. Again, as I have said, depending on where you are located on the globe and in which season, but generally it is assumed if you are on the equator in the noon time, the sun would be your overhead and no shadows would be there. So, you can simulate with the low angle sun or high angle sun as per your requirements. Now, how hillside is calculated, some indications I have already discussed or told you, that indicated that to calculate the shade value, first the altitude and azimuth of the illumination source are needed. So, these are the two inputs along with your input digital elevation model, and these values will be processed with the calculations for slope and aspect to determine the final hillside value for each cell in the output raster. So, if you are using a tin and creating a hillside, because tin by itself is carrying slope and aspect map, and therefore, this hillside product will be created very quickly. Whereas, in case of typical raster, inside in the background it will calculate slope and aspect, and based on that then hillside values will be calculated. And the algorithm for calculating the hillside value is, which we have also touched little bit, like a 255 here, because we are keeping the range between 0 to 255, and cos zenith radian, that is the angle radian, we will discuss little later what is that, and then multiply by cos slope radian, that the value of the slope degree, and of course the zenith, and the sin zenith means aspect, and then cos azimuth, and all this will be put. So, everything is being multiplied except here you are having the plus sign. So, once that is done for both directions, now that if the calculation of hillside value is less than 0, the output cell will be 0. So, because in that case, so that is why we multiply by 255. Now, the radian, as you are seeing on the left side, what is it is this GIF file or this simulation is showing what is basically radian is that the radian is equivalent to the angle subtended at the center of the circle by an arc. So, this arc which we are talking, and this is the radian, and this is which is always 57 degrees, because this is equivalent to radius. When we convert this radius into arc, so then this angle becomes always 57 degree. Now, this one becomes 2 pi, and whole circles that angle, that means this one becomes the half becomes pi and whole one becomes 2 pi. So, mathematically to find the angle subtended in arc, the angle subtended by arc divided by 360, that is arc length divided by 2 pi r, and then arc of a circle with the same length as the radius of the circle subtends an angle 1 radian, as you are seeing currently here, and the circumference subtends an angle of 2 pi radians. So, if you are covering the entire circumference, then the radian value would be equivalent to 2 pi. So, that is why in that calculation there, what we are finding, the values are always in radians. Anyway, now option available say in standard GIS software about the hillside. Most of the time I am using examples from ArcGIS or ArcView. The reason is because I am using these softwares, but that I am no way I am promoting this software. It is your choice, but for examples I have to show through some software. Since I am comfortable with this software, so I am showing. But from commercial angle point of view, there is no promotion of this software. Please, I would definitely suggest start using these public domain softwares or open source softwares like QGIS. There is no problem. But since I was or I am hooked to this ArcGIS, so I always take example from that. Now, here what you have to provide for hillside: input, output, and these are the two default values which I was mentioning. Automatically these values will be prompted. However, you can definitely change these values, but by software it is always put as these values, and Z factor also in the default is 1. So, you have to take care about Z factor as well, and once you do it, you can do it. Now comes about this discussion about the multi-source, multi-illumination source instead of one. Is it possible? Now it is becoming possible. I will show you some examples and the utility of also multi-directional hill shading, or in short we say MDHS. Now this because the traditional shades are created illuminating light from only northwest direction. Though I can create from any direction by changing the angle in my software, but always it would be a single direction. But if I want to create a shaded relief model having multiple direction, that is MDHS, then how to do it and how this concept works. So, this single direction will always produce illuminated sites which are overexposed, and the terrain details of non-illuminated sites are obscured or goes in darkness. So, that is the disadvantage if I am having one single illumination source. I gave the example of a cricket pitch or football ground. In the night time when these are held, these matches are held, generally you see there are 4 shadows because 4 illumination source, and none of these shadows would be as strong as in case of single shadow. So, your terrain may look completely different if I am having multi-directional illumination source or multi-directional hill shading. The issue persists even more in areas with medium to high slopes. There only we require many times this hill shading, and the problem is becomes obvious in case of hilly terrain. So, this in Brussels 1974 started working on this, recommended setting a variable light source, multiple light source for each cell based on a primary illumination direction, that is plus minus a directional adjustment computed from the aspect of the cell. Even in the first part when we are having the single source illumination, there also slope and aspects are. So, aspect and slopes plays very important role even if you have to calculate hill shading, whether it is a single illumination source or multiple directional. Now, this scientist Brassel also recommended that illumination inclination angle, that is how high the sun is for each raster cell, should be variable. So, not only the direction, but the elevation of the sun between 0 to 90 degree, that should also vary based on the derivation of the surface normal to primary illumination source. So, if a sloping surface is like this, then this would be the normal. So, based on that normal, this illumination angle. So, every time what this illumination source for each cell is doing, it is calculating illumination and surface normal for each sloping surface, and accordingly it is keeping the illumination elevation or the source elevation accordingly. So, keeping this thing as surface normal. And then this method developed by Brassels, every cell would receive a hillshade based on a different illumination angle. So, in case of single source illumination or in a conventional hill shading, what we do? We keep both things constant, that means illumination direction as well as elevation. But here things are changing, not only one single direction, multiple direction one, and another thing, this height of illumination source, that in terms of elevation angle we are also changing for each cell as per their inclination or creating a surface normal. So, however, so far this has not been implemented in various softwares, but there are some examples. Indirectly definitely you can do it, but direct menus you may not find in any standard software. Of course, indirectly one can do it without much problem. Whereas others like Robert Mark's multidirectional oblique weighted MDOW method, that is through Mark 1992, has been implemented. So, the Barrett's method has not been implemented, but this one has been implemented. The only difference is both are multidirectional, fine, similarity is fine, but this is obliquely weighted, there it is based on the surface normal. Now, MDOW method is the landscape is illuminated from 4 directions, each separated by 45 degree and covering a range of 135 degree, like here. Like here what you are seeing, that 45, so this is 180 degree, then again another 180 degree, total is 360 degree. So, aspect deviation from the illumination source and the weights are given. So, if they are in the 90 degree, then maximum weight, if it is 180 degree, this is minimum weight, keeping that illumination is coming from say one particular direction. So, if there are 4 directions, we will illuminate from all directions. So, this direction, this would be and that would be also. 0 and 360 degree in a whole circle is the same. So, by this method the hillshade generated by each these illumination sources is then weighted according to aspect of that cell. So, Brassel's method and Mark's methods are, this is the major difference they are having. Illumination source are multiple, no doubt, but this here both are using aspect, but little differently. Now, this cumulative effect produces a hillshade illuminated generally from average of 4 illuminations directions, and the graph which I am going to show here may look little complicated, but let me explain that this is the illumination source 1, and what we have said that illumination source is coming from 4 directions and each separated by 45 degree, covering an range of 135 degree. So, in this figure which we are seeing, each covering a 45 degree. So, this is 45 degree and this is what it is covering by illumination source 1, this is illumination source 2, this is illumination source 3, and then it is illumination source 4. So, angle from, of course, this is total 180 degree, but if we take the value from here and here, this would be 135 degree only. So, this much it will cover. So, this is based on the Marx's original idea, which shows that the weighting of all 4 illumination sources, and they are only in the western hemisphere on the deviation of the cell's aspect values from cumulative direction illumination. So, this is how these are done, and weighting factors for illumination source are also given here. Now, when we go for analysis, and by modeling and the shade, one calculates the local illumination and whether the cell falls in the shadow or not also. And by modeling shadow, one identify each cell that will be in the either shadow or will be illuminated at a particular time. So, if we want for different timings of the same terrain and digital elevation or hill shades, say starting from morning to evening, you can keep changing the sun position and then can create a simulation about how a terrain will, the shadows varies or changes with throughout the day. So, in that for this analysis of hillshade, the cells that are in the shadow and other cells are coded 0, all other cells coded with the integers between value 1 to 255, because this will always create a grayscale product, though you can by some techniques you can create a colored one also. So, one can reclassify all values greater than 1 to 1, producing a binary output raster also. Like here hillshade analysis, and this is soil map with hillshade, simple hillshade, one directional and soil map. If you overlay like this, what the advantage? Immediately you would realize that there is a relationship between soil and landforms. So, it is very useful that a hillshade to raster and show the terrain support other information. So, correlation between an elevations or landforms and a soil map can be found very easily. Similarly, with the geology, similarly with the many chemical qualities, many things can be seen. Now, as I have been mentioning that you can by some employing some tricks or techniques, you can always create a hillshade of even in color, though original output would be in the black and white. So, here again the same digital elevation model which we have been taken in our examples, I have created a black and white hillshade, then colored hillshade is also here, because this has the top one DM has been assigned a color ramp and hillshade has been kept in the background, and this DM has been kept at 50% transparency. So, both are being displayed here in. So, ultimately what you are seeing is a hillshade in color. So, it is more useful in that one. Also, I just for convincing that everything was done correctly, if you overlay a drainage network, these should go in the valleys. That is the one way of checking that all angles and everything was fine while creating a shaded relief model. And as I have been saying that these hillshades, whether multi-directional, single directional, are very useful for various purposes. Here what you are seeing, this is example of St. Andrews faults, very seismically active regions of the world, and here we are having our in India, this falls in seismic zone 5, the Kutch region. Again you are seeing hillshades in the background, and then you are having other information top of that. So, these if I would have represented the St. Andrews faults in a plain digital elevation model without hillshade, that may not be very convincing, but here it is very much convincing that faults are creating a depression because of such movements are there and high erosional activity. Lot of outputs or presentations people do, in which they keep always a shaded relief model in the background, like done here also in case of SAR interferometry based studies of ground deformations, which were because of an earthquake which occurred on 12th May in Nepal of magnitude 7.3. So, instead of presenting your work in with simple thing, if you can bring a cedar leaf model in the background and put that layer on top, it is more interesting and convincing also. One more example of another earthquake which occurred, that was on the 12th May, that was on this one Kathmandu one was on 25th April, and again in the background you are having cedar leaf model. Now, this is the comparison between a single directional hillside versus a multi-directional hillside. And so, here you can see very clearly that a lot of features, landforms, ground features which we have been completely missing in single direction hillside are becoming obvious in multi-directional hillside. So, definitely those people who have been using single directional, if these becomes very easily producible using standard softwares, then people would definitely go for multi-direction. Because if I have to do the simulation, that means simulation I am putting the sun in northwest direction, then question will come, why only in the northwest direction, why not in other direction, why not multiple illumination source. So, if we do that kind of work, we can produce much better hillside than a single direction one. So, this one is a completely expressionless region, whereas this and extenuates minor details in the terrain as compared to the traditional one. So, this is bringing really minute details about the terrain. Now, there are further advantages of multi-directional MDHS, that a hillside presents an unparalleled view of the world's mountains, plateaus, valleys and canyons, and by varying the direction of the light from 4 different sources, and terrain depicted by multi-directional hillside is more realistic representation, because here it is the balancing is being done between overexposed and non-illuminated or underexposed surfaces. This MDHS also enhances the expressionless region we have seen in the example and extenuate the minor details in terrain as compared to the single directional one. And by adding this hillside layer to your map, basically as I have been discussing, your presentation becomes very convincing, very clear. I gave the example of St. Andreas fault or Bhuj or Kutch region, and instantly people will feel very convincing and they may show very much interest, and it provides a clear context and increased local understanding of how your subject fits in the surrounding. So, if it is part of a highly rugged terrain, immediately that feeling will come, but in a simple digital elevation model, that ruggedness of the terrain, that feeling will never come, that perception will a user will never develop. This is another example of hillside where the faults and rivers have been used, valleys and edges and mountain. So, in the background a hillside is there and this is what you see. So, lot of atlases nowadays which are digital or analog, they are also doing this thing, not only in subject of civil engineering and earth sciences, but in geography also. Extensively now hillsides are being used, and if it is possible to generate multi-directional, that would be much better. So, because you know that if I can produce a hillside, then mountains may look eternal, but in fact they have been saved over millions of years by the interplay between tectonic forces and water erosion. So, these things keep happening, and especially in like young mountain chains of Himalaya, and so these two forces are very much active there, and this relationship becomes clearer when hillside juxtaposed with the rivers or faults. That is why I was saying that for presentations it is always, if possible, bring a hillside in the background and then plot your data. It would be more interesting, more convincing, and audience can immediately feel that what is the ruggedness of the terrain. Hillside is also useful when displaying the relief of mountainous region, for plain areas also. Like for example, hillside in a single direction illumination source, hillside is a multi-directional hill source. And this is Mount Rainier, very famous landform or landscape of Washington DC region, and there you can see that what the advantages of multi-directional. All minute details are there. This is Alps example, very close to Himalaya, not physically but terrain wise, though the ruggedness is not as high as in Himalaya, but if I remove this caption, somebody may feel this is a part of Himalaya. That is why I said very close to Himalaya. And it will give you a very clear picture immediately without much. You do not need much training if things have been represented through hillside multi-directional. If somebody is working on glaciers, avalanches, again if they are put in the background, you are having a multi-directional hillside put over is glaciers or avalanche sites or snow covered area, immediately things becomes very, very clear. This is the multi-directional hillside which I have created using this MDH or this earlier method, though this is not because it is covering a large area and therefore you are not seeing much details, but if you zoom any part and compare with the conventional one, you would really appreciate that what is the advantage of having multi-directional hillside. Now very few more minutes I would take in this discussion is how to exploit further these hillside, which we have done to remove false topographic perception phenomena. And like here on the left image, a satellite image is there. I have also written the sun azimuth and elevation angle. And what happens here, that because the sun is in the southeast quadrant when this satellite image was taken, and therefore it is giving wrong perception about topography or existence of false topographic perception phenomena, FTPP. And because of that you might be feeling that this Bhagirathi river, which is part of the or tributary of the Ganges, is flowing on the ridge. That means it is wrong perception. A river cannot flow on the ridge. Topographically or geomorphologically it is not possible. So that is something wrong in our perception. How can we get rid of this wrong or FTPP from our satellite image? So what we did, we exploited the shader relief model and created a shader relief model, corresponding shader relief model using opposite sun azimuth and illumination. So sun illumination was added 163.3 degree, it was added 180 degrees, so it becomes 343.3 degree, and elevation angle was kept at the same. And then when the same terrain, a digital elevation model of this corresponding satellite image was used and illuminated from northwest direction, then you see that the river is flowing in the valley. But this is not the true representation as satellite image is doing. So with employing digital image processing techniques, we can do color transformations and can bring other characteristics of satellite images over this shaded relief model, having opposite illumination direction as compared to your satellite image like here. So here this is not suffering from FTPP and it is bearing all the content of your satellite image and your river is flowing in the valley, at least it is being perceived that it is flowing in the valley. Note in the previous example that here it is being perceived that it is flowing on the ridge, which is incorrect perception. Here your perception will improve. So removing a false topographic perception phenomena, we can definitely employ a digital elevation model. And there are other examples that this is digital elevation model, this is shadow relief model of the same area, then this is the image, and this one has been created using again sun illumination which was here. We have forcefully sent here in the northwest direction, and when color transformations were done, you get a corrected FTPP corrected satellite image. Now two animations, these are the last and then I will close. There I am depicting these two sun parameters like elevation and azimuth. First I will be depicting the azimuth and then how the changes which elevation can bring in our perception. So, first changing the azimuth here. What you are seeing here, the white one is the sun. So, this when sun is in the northern hemisphere, so I say this is northern hemisphere, this is southern hemisphere. So, when the sun is in the northern hemisphere, I am not seeing false topographic perception phenomena, I am not observing that. But once the sun comes in the south and southern hemisphere, I start seeing this FTPP. So, that is for that purpose only, because each satellite image which is being acquired by sun synchronous polar orbiting satellites of any part of the globe, earth, moon or Mars, all of them are suffering from FTPP. So, FTPP is a universal phenomena, and therefore, before satellite images are put for interpretation or further analysis, it is always that one should one should exploit this technique of hill shading and remove this FTPP from the images. So, here there are 8 images, 4 images are without FTPP and 4 images when the sun is in the southern hemisphere are suffering from FTPP. Now, another simulated animation is starting the sun elevation is of course, the sun is kept here, but elevation is being changed from 5 degree to 90 degree. So, when sun is near horizon, that is 5 degree, you see a very dark image, and when sun comes overhead you see the brightest. But important point is also your depth perception changes. When the shadows are large, your depth perception is more. When shadows are less or no shadow, your depth perception is different. So, that means the illumination source, azimuth and elevation plays very important role about the depth perception of satellite images or of a hillside. So, these things while creating or using or interpreting, one should take care about these things and should develop a very good understanding about this, as I have explained. With this, I thank you very much.